Hello, welcome to this video. In this video, let us derive an efficiency equation for a Carnot cycle. Now, what is so special about Carnot cycle? Carnot cycle is the one cycle which is best known for its highest efficiency, or you can say Carnot cycle is the one which gives you highest efficiency between any two temperatures. Now, why it is so, we will have to discuss. Imagine there is a cylinder and piston arrangement, and we are talking about, of course, a closed system, and there is air inside this system. Okay. Now, we are talking about the first figure where there is a piston and cylinder arrangement, and it is arranged in such a way that this cylinder head can be replaced by an energy source which is at some temperature, and we can add the heat from external source. All right. Now, energy source, let us say the temperature of that energy source is TH. Okay. Now, we are adding the heat at a constant temperature. Okay. That is what is very important for a Carnot cycle. So, let me write PV as well as TS diagram. Meanwhile, we will write PV as well as TS diagram. So, this is our pressure versus volume diagram and temperature versus entropy diagram for a Carnot cycle. Now, let us say we are adding the heat at constant temperature. Now, that is quite difficult to imagine, because the moment we add the heat, what will happen is that the piston tries to move towards right side, and temperature obviously will drop. But however, it is assumed that the temperature of this source and temperature of this the air which is absorbing the heat, both are at same temperature. Now, it is obvious that the heat transfer occurs only when there is temperature difference, but however, there is an irreversibility which we talked in basic thermodynamics. The temperature difference is also an irreversibility. So, whenever there is a temperature difference is there, so there will be losses. So, if you assume that the temperature is very small between the source from which we are taking the heat, then only we can say that there is negligible energy loss or negligible irreversibilities. So, we are assuming that from somewhere here, let us say point 1 or state 1, from here the heat is added at constant temperature. Now, that is what makes this cycle highest efficient one, because it is internally reversible. So, the process of adding heat and rejecting heat, if it happens at constant temperature, you can say that literally there is no losses. So, we will have heat addition is happening at constant temperature. Now, obviously, piston moves towards the right during this heat addition process, and the same can be represented in our TS diagram as well. So, heat addition is at constant temperature. So, in a TS diagram, constant temperature will be a horizontal line towards right, because entropy increases with the addition of heat. Now, one can argue, even though we are adding heat, why the temperature is not changing? That is what we are saying. So, even though we are adding heat, the temperature remains constant. So, that is the what we are saying, that there is no losses, there is no irreversibility. All right. So, as soon as the heat is added, the piston is moved to an extent where the amount of it is equal to the amount of heat added. So, temperature remains constant. Now, 2 to 3, we remove this source, and we again insulate this side. So, then we allow this air to expand. So, we will have 2 to 3 is a polytropic expansion, isentropic expansion. Now, remember this we have talked the nature of curves in the last class. For an isentropic or adiabatic process, the nature of curve will be little steeper than temperature process, all right, constant temperature process. So, 2 to 3 is an expansion process in a reversible adiabatic process. Now, here in TS diagram, you know that it is going to be a vertical line, because Isentropic means entropy constant. So, this will be entropy constant or PV power comma constant. So, temperature constant, alright. Now, again during process 3 to 4 we reject the heat to a lower temperature sink. So, it has to be again constant temperature heat rejection process. So, it will be parallel to the line which we had drawn earlier. So, it is constant temperature heat rejection process. So, this will be heat rejection QR, alright. So, in a TS diagram, we will have the similar constant temperature line where temperature is constant and heat is rejected. So, here heat is added, here heat is rejected. And we will go back to the initial point. After all, it is a thermodynamic cycle. So, then what we do is that we take out this sink and we will bring it back to 1 according to the process reversible adiabatic or PV power gamma is equal to constant or entropy is constant or entropy is constant. So, now we have a complete cycle where 1 to 2. So, we can write this where 1 to 2 is isothermal that is constant temperature heat addition. Alright. Now, 2 to 3 is reversible adiabatic or isentropic expansion. Okay. Now, 3 to 4 is again isothermal, that is constant temperature isothermal heat rejection. So, that is again constant temperature, and 4 to 1 is again reversible adiabatic or isentropic compression. Okay. Now, we are interested in deriving efficiency equation. Now, what is efficiency is given by? Efficiency is given by work net divided by heat supplied, output divided by input. Desired output is work net and input is heat which we are supplying. Now, work net can be rewritten as heat supplied minus heat rejected. Now, this is coming from first law of thermodynamics. For a closed system is summation W is equal to summation Q. So, Qs minus Qr by Qs, or we can also write it like 1 minus Qr by Qs. Okay. Now, this equation can be simplified. Now, remember process 3 to 4 is where we are talking about heat rejection, right. So, process 3 to 4 is where we are talking about heat rejection. Now, what will be Q 3 to 4? Q 3 to 4 will be equal to, remember this is reduced from our first law of thermodynamics. So, Q minus W is equal to delta U. So, if you are applying this between 3 and 4, this will be the equation, but for constant temperature process this will be 0. Okay. Therefore, Q is equal to W. Now, what will be W equation for constant temperature process? P3 V3 ln of V4 by V3. Now, this is very important that many students make mistake here. Now, this will be negative. This Q3 to 4 will be negative obviously because our W3 to 4 will be negative, because we are talking about a curve where we are coming from right to left. So, that means volume is decreased. So, V4 will be less than V3. So, but remember we have already used the negative sign here, okay, already used negative sign for QR. So, obviously we cannot substitute negative of negative, alright. So, it is something like I have given 1000 rupees to somebody and he has spent let us say 500 rupees. Now, I am asking the balance, okay. Now, I have used this equation already that the money which I have given as plus. So, money given minus money spent, money spent, money given minus money spent. So, here if I use it something like 1000 minus of minus 500, this will be wrong, right, 1500, no, because you are already using negative sign here, this has to be substituted positive. So, you cannot say that minus 500 because minus is the amount which I spent, I am using negative sign. So, it has to be carefully written. So, whenever we are already using negative sign there, it is our duty to substitute it as positive. So, Q3 to 4 let us call it as heat transfer, but when I say heat rejected, I will make this equation positive. So, make it positive. So, QR is equal to P3 V3 ln of V3 by V4. If you do this, this will be positive. Now, I will come back to this equation 1 minus P3 V3 numerator ln of V3 by V4, okay, divided by, now let us go for heat supplied. Heat supplied is happening between 1 and 2, right. So, between 1 and 2, process 1 and 2, Q1 and 2 will be similarly our W1 and 2 both are equal. So, P1 V1 ln of V2 by V1. So, here we do not have any doubt. So, it is positive only and we will keep it as it is P1 V1 ln of V2 by V1. So, remember when we talk about Q3 to 4, we are talking about transaction, it could be negative or positive. But the moment I write QR, I want to keep it positive because already I have used negative sign there. So, QS is P1 V1 ln of V2 by V1. Here there is no doubt V2 is greater than V1, so we will get positive. So, it can be rewritten as P1 V1 ln of V2 by V1 in this equation, alright. Now, these two are going to be cancelled out. V3 by, because we will prove it, V3 by V4 is equal to, because V3 by V4 is equal to V2 by V1, we will prove this, okay. Therefore, now our equation reduces to 1 minus, now I write this P3 V3 is equal to MRT3, that should not be a problem because PV is equal to MRT, we are talking about an ideal gas, PV is equal to MRT and this will be MRT1. So, MR cancels out and we will have 1 minus T3 by T1. Now, go back here. Now, what is this T3 and T1? Now, this is our T3 is equal to T4. So, this is our lower temperature, the temperature at which you are rejecting the heat to. Similarly, here temperature at which heat is supplied. So, TH is equal to T1 is equal to T2, correct. So, TL is equal to T3 is equal to T4, correct. So, same is true here. This is our TH heat supplied, this is our TL heat rejected, temperature at which heat is rejected. Now, this can be further written as, now T3 is TL and our T1 is TH. So, this is nothing but efficiency is equal to 1 minus TL by TH, okay. Now, this is our equation for efficiency of a Carnot cycle. Now, it depends simply on the temperature at which heat is supplied and heat is ejected. So, if at all you want to find out the highest efficiency between two given temperatures, you will have to use this equation. Now, let us prove that V3 by V4 is equal to, let us prove V3 by V4 is equal to V2 by V1. Now prove V3 by V4 is equal to V2 by V1. Now consider, let us consider the process 1 to 2, sorry 2 to 3. Let us consider 2 to 3. So process 2 to 3. So what we can write is P2 V2 power gamma is equal to P3 V3 power gamma, correct? So because PV power gamma is equal to constant, so PV power gamma is equal to constant. Now what we can write is I am interested in temperature and volume ratio because pressure has nothing to do here. So I will go for eliminate pressure. So PV is equal to MRT and say that in place of pressure I am going to substitute T by V. Okay. So in place of pressure, if I substitute T3 by V3, V2 power, sorry, this is T2 by V2, V2 power gamma. In place of P3, I will substitute T3 by V3, V3 power gamma. Now T2, V2 power gamma minus 1, T3, V3 power gamma minus 1. Okay. Now we have got an expression where we can write it like we would like to prove what V3 by V4, right? So V3 by V2, I will keep it in the form of V3 by V2, that would be good. So say V3 by V2 power gamma minus 1 is equal to T2 by T3. And remember what is T2 and T3? T2 is TH, T2 is TH. So this will be TH by TL. This will be TH by TL. Now I will send this to the other side 1 by gamma minus 1. So V3 by V2 we have got an expression TH by TL whole power 1 by gamma minus 1. Now similarly let us take the other part like the other side. What is the other side? The other side is process 4 to 1. Similarly, let us take process 4 to 1. Now similarly process 4 to 1. Process 4 to 1 we can write P4 V4 power gamma is equal to P1 V1 power gamma. All right. Now I want to eliminate as usual pressure here. PV is equal to MRT. I will use in place of pressure. I will use MRT by V. So T4 by V4. V4 power gamma is equal to T1 by V1. V1 power gamma. So T4 V4 power gamma minus 1 is equal to T1 V1 power gamma minus 1. So we can write like TH by TL, that is what we would like to write. So T2 by T1, that is what I will try to write. So T1, I will keep this here T1 and I will try to send T4 here. So T1 by T4 is equal to V4 by V1, okay, whole power gamma minus 1. Or we can say this T1 is nothing but TH, right? So T1 is TH, T1 is TH and this is TL, okay, and this is V4 by V1. This I can send it here 1 by gamma minus 1. Now look at these two expression 1 and 2. What we have is that this TH by TL common, right? So TH by TL. So therefore from 1 and 2, we can do what? We can write that V3 by V2 is equal to V4 by V1. So we wanted to prove V3 by V4. What we do is that we send this to the other side. V3 by V4 is equal to V2 by V1. Okay. So hence we have proved that this ratio can be cancelled out in our expression. All right. So whenever we talk about Carnot cycle, remember that is the one which gives us highest efficiency because that there is the temperature at which heat is added, and it is an isothermal process. So, heat added and heat rejected, they are isothermal. So, one factor which makes this cycle is highest efficient because of the same reason, that whenever we have a difference in temperature, that is the cause of irreversibility. So, if we are supplying heat at constant temperature, so there is very less temperature difference, very less temperature difference between the source and the air where you are receiving the heat. So, irreversibility is not there. So, there is no losses. That is why we get highest efficiency in a Carnot cycle. Thank you.